Hello and good afternoon friends, welcome once again to the CEC-UGC live lecture. Dear friends, as you know that we are carrying a series in the subject called chemistry, and the name of the series is Chemical Reactivity and Mechanism. Under this series we have conducted various lectures, and today also we would be continuing this very series further. In previous session, that is in our previous lecture, we discussed about the derivatives of carboxylic acids, and under this very topic we discussed about the acid anhydrides as well as acid halides. Today we are going to discuss about acid esters and acid amides. We would be discussing about the preparation, reaction and uses of acid esters and acid amides. And for this we have again with us in our studios Dr. Vandana. Dr. Vandana, as you all know that she is assistant professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, let's take advantages from her experiences and try to gather maximum information, maximum knowledge through this EduSet lecture of ours with the help of her immense knowledge. So first of all, I would like to welcome our guest Dr. Vandana. Dr. Vandana, welcome to the EduSet lecture. As we have already discussed with the acid anhydrides as well as acid halides, which are the part of the carboxylic acids, if I am not wrong, as you already mentioned. And today we would be discussing the other two, that is the acid esters and acid amides. So over to you, ma'am.
Thank you so much, ma'am, and good evening viewers. As we have already discussed about the derivatives of carboxylic acid, there are mainly 4 kinds of derivatives of carboxylic acids which can be produced by the substitution of hydroxyl group of carboxylic acid by halogen, by anhydride group, by alkoxy group or by amino group. So we are having 4 kinds of derivatives of carboxylic acid: acid halides, acid anhydride, esters and amides. In the last lecture I have explained about the 2 derivatives of carboxylic acid, that is acid halide and acid anhydride, about their preparation, about their reactions, about their uses. In this coming lecture series of this derivatives of carboxylic acid, today I will take the rest 2 derivatives of carboxylic acid, that is esters and acid amides. As you know, the structure of derivatives of carboxylic acid, you can see the slide. There are 4 different kind of carboxylic derivatives in which acyl group is common. Which is acyl group? RCO. And what about the preparations and reactions of esters of carboxylic acid? Esters are the derivatives of carboxylic acids in which hydroxyl group of the carboxylic functional group has been replaced by an alkoxy group or an aryloxy group. You can see the alkyl esters and aryl esters, the structure, where AR is the aryl group or R is the H or alkyl aryl group. Alkyl alkanoids have the general formula CnH2nO2, which is the same as that for the alkanoic acid. Esters of carboxylic acid are widely distributed in nature. The volatile esters have pleasant smells. They contribute to the flavors and fragrances of the fruits and flowers. Oils and fats are the triesters of glycerol with higher fatty acids such as stearic acid, you can see the structure, palmitic acid and oleic acid. Waxes are the naturally occurring esters of long chain fatty acid, carbon 16 or greater chain with long chain alcohols. Beeswax obtained from the honeycomb of bees is chiefly myrcene palmitate. Spermiceti, a wax that separates from the oil of sperm whale on cooling, is chiefly cetyl palmitate. You can see the chemical composition of cetyl palmitate. Cetyl alcohol is hexadecan-1-ol. Cyclic esters are called lactones. You can see the structure. There are intramolecular esters derived from cyclodehydration of open chain hydroxy acids. Gamma and delta hydroxy acids undergo spontaneous lactonization to yield stable gamma and delta lactones respectively. You can see the structure. how gamma hydroxybutyric acid will give you gamma butyrolactone. You can see the cyclic esters, you can see the oxygen in between the cycle, and delta hydroxyvaleric acid will give you delta valerolactone. Now the next heading is the nomenclature of esters. The esters consist of two words, first name alkyl or aryl attached to the oxygen of the ester, and the second word is the name of the parent acid in which the ending ic of the carboxylic acid has been replaced by ate. This nomenclature applies for both common as well as for IUPAC nomenclature of esters. You can see the common name in the brackets or in the parenthesis. There are some structure with their IUPAC and common name, like methyl methanoate, common name is methyl formate, ethyl ethanoate, ethyl acetate, methyl propionate, 1-methyl ethyl 2-methyl propanoate, isopropyl isobutyrate, and the others are also there. Next is the preparation. How can we prepare the esters? From carboxylic acid with alcohols. Esters are generally prepared in laboratory by heating carboxylic acid with alcohol in the presence of a small amount of sulfuric acid or dry hydrogen chloride gas. This reaction is known as Fischer esterification reaction. The reaction is reversible, and hence alcohol is generally taken in large excess to forward the equilibrium towards the product. So, if you want to produce the product, you have to take the large amount of alcohol, and you can back the reaction also by changing the amount of ethyl acetate and acetic acid. So, it is an reversible reaction. You can see how acetic acid react with ethyl alcohol to give ethyl acetate, and benzoic acid will give you methyl benzoate. The rate of esterification is sensitive to the steric hindrance near both the carboxylic group and hydroxyl group of the carboxylic acid and alcohols respectively. Therefore, the order of esterification towards carboxylic acid will be, you can see, more the number of alkyl group, less will be the reactivity. Then reactivity of alcohols toward esterification, you can see the reactivity will decrease when the alkyl group will, the tertiary alcohol or secondary alcohol, the number of R group will increase on alcoholic group. Phenyl esters are not generally prepared from phenols and carboxylic acid because equilibrium favors the reactant side rather than the product side. Esters are more readily prepared in good yield by the reaction of carboxylic acid with alcohol in the presence of DCC. What is DCC? Dicyclohexyl carbodiimide. DCC is a powerful dehydrating agent and gets converted to dicyclohexyl urea on taking up water from reactant molecules, and you can see how DCC react with carboxylic acid and alcohol to produce NN-dicyclohexyl urea. Next, by the acid chloride when react with alcohol and phenols. Esters are more readily prepared in good yield by the reaction of acid chloride with alcohols and phenols. The reaction is generally carried out in the presence of pyridine to neutralize the HCl which has been formed in the reaction. There are certain reactions like acetyl chloride, benzoyl chloride and acetyl chloride with phenol, and the products are methyl acetate, ethyl benzoate and phenyl acetate respectively. Next, from the acid anhydride with alcohols and with phenols. Esters are also prepared by the reaction of acid anhydride with alcohols and phenols. The reaction is generally carried out in the presence of pyridine which neutralizes the carboxylic acid formed as a co-product. So, you can see the reaction. Acetic anhydride when react with ethyl alcohol in presence of pyridine, ethyl acetate as well as pyridinium acetate will form, and when this acetic anhydride react with phenol, it will give you phenyl acetate with pyridinium acetate. Next reaction from carboxylate salt and with alkyl halide. Sodium, potassium and silver salts of carboxylic acid react with alkyl halide to give the esters. However, it is restricted to primary alkyl halides and unhindered secondary alkyl halides. Tertiary alkyl halides undergo dehydrohalogenation to give alkenes. The reaction gives good yield of esters when carried out in a polar aprotic solvent such as DMF. What is DMF? You can see N,N-dimethyl formamide and hexamethyl phosphoric triamide, which is HMPT in a short form. So, you can see the reaction sodium acetate when reacts with ethyl bromide in presence of DMF undergoes SN2 mechanism to give ethyl acetate, and sodium benzoate will give you methyl benzoate. Alkyl sulfonates and dialkyl sulfates may be employed in the place of alkyl halides. So, you can see potassium acetate when react with ethyl tosylate, TS tosylate, it will give you ethyl acetate and potassium tosylate. What is the structure of tosylate? You can see sodium benzoate when react with dimethyl sulfate, it will give you methyl benzoate and sodium methyl sulfate. Next preparation is from the carboxylic acid with diazomethane. Azo word is due to for nitrogen. Methyl esters of carboxylic acid can be conveniently prepared by the reaction of carboxylic acid with diazomethane in ether solution. Acetic acid will give you methyl acetate, while benzoic acid will give you methyl benzoate. Next preparation from carboxylic acid with alkenes. Carboxylic acid react with alkenes in presence of H2SO4 or phosphoric acid. The addition will take place according to the Markovnikov rule, and it is particularly useful for the preparation of tertiary alcohols. You can see acetic acid when react with isobutylene, an alkene, will give you tertiary butyl acetate. Next is the Chemical reaction. Aldehydes on treatment with aluminum ethoxide undergo a bimolecular reaction similar to Cannizzaro reaction to yield the esters of type RCOOCH2R. Ethyl acetate can be prepared commercially by this method. So, acetaldehyde react with acetaldehyde will give you ethyl acetate. Now, the physical properties of esters. Esters of low molecular mass are colorless liquid having fruity smells. Boiling point of methyl formate, methyl acetate and ethyl acetate are respectively 32, 54, 57 and 77 degrees Celsius. Esters of relatively high molecular mass are colorless solids. The boiling points of methyl and ethyl esters are lower than those of corresponding parent carboxylic acids and also the carboxylic acids of the same molecular mass. The reason is that carboxylic acid form intermolecular hydrogen bond, but esters do not form. Methyl formate and ethyl formate are fairly soluble in water. Ethyl acetate is slightly soluble. Esters of high molecular masses are almost insoluble in water, and most of the esters are soluble in organic solvents. Here are the examples of organic solvents like alcohol, ether, benzene, chloroform and acetones. Now, the next main heading for the esters are the reactions of esters. Like the acid chlorides and anhydrides we have discussed in the last lecture, esters also undergo nucleophilic acyl substitution reaction. What is that? Nucleophilic means a nucleophile has to attack on this esters and anhydrides and chlorides and amides, and acyl group is common. RCO substitution will take place by the incoming nucleophile. So, nucleophilic acyl substitution reaction. Why these give nucleophilic acyl substitution reaction? Simply because they are the better living group. When the groups are weak bases, they are the better living group. However, esters are less reactive than either of them. Esters also undergo condensation reaction that involve alpha hydrogen atom. We have already discussed in the last lecture the comparison of reactivity among all 4 derivatives of carboxylic acid, that is halides, acid halides, anhydride, esters and amides. First reaction I am taking here the hydrolysis. Esters are hydrolyzed by heating with water in presence of small amount of H2SO4 or HCl to give the carboxylic acid with alcohol. This is a reversible reaction. So, it can take place many hours to reach the equilibrium and never goes to completion. So, the yields are about 50%. You can see after hydrolysis ethyl acetate will give you acetic acid with ethyl alcohol, and methyl benzoate will give you benzoic acid and methyl alcohol. Esters are hydrolyzed preferably by heating with a dilute alkali. Since the reactions are almost irreversible, occur rapidly and give almost quantitative yields. The products are carboxylate salt along with alcohol. The free carboxylic acid is obtained after acidification of the reaction mixture. The hydrolysis of esters with alkali is called saponification because soaps are prepared by hydrolysis of fats with alkali. So, there are 2 reactions, ethyl acetate on hydrolysis with NaOH, that is alkali, will give you sodium acetate, salt of acetic acid and ethyl alcohol. Methyl benzoate will give you sodium benzoate along with methyl alcohol. Lactones are hydrolyzed by alkali to give the carboxylate salts of hydroxy acid. So, you can see the reaction, gamma valerolactone will give you sodium gamma hydroxyvalerate, which on hydrolysis will give you gamma hydroxyvaleric acid, and after heating it will give you gamma valerolactone, a cyclic ester. Next reaction is the alcoholysis. It is also known as transesterification. Why transesterification? When an ester is heated with an excess of another alcohol in the presence of acid or a base as a catalyst, new ester will form. So, one ester will give you another ester. That is why it is known as transesterification. It is produced as a result of exchange of alkoxy group, that is OR dash group of the ester with the alkoxy group of the reactant alcohol. Such a reaction that result in transformation of one ester into new ester by the action of alcohol is called a transesterification reaction. In the reaction you can see there is also example, ethyl acetate when react with methyl alcohol, it will give you methyl acetate, that is ethyl group will be replaced by methyl group or transesterification is there. Another example is there, methyl benzoate when reacts with normal butyl alcohol, it will take the alcohol in excess to shift the equilibrium towards the product, that is towards the normal butyl benzoate. Next reaction is the gamma butyrolactone. Again we are taking the excess of methyl alcohol to shift the equilibrium towards the product, that is methyl gamma hydroxybutyrate. Next reaction is the isopropenyl acetate with glycerol to give the triglyceryl acetate along with acetone. Next reaction is the reaction with ammonia, or we can say ammonolysis. Esters react with ammonia and amines. Amines can be primary, that is 1 degree, can be secondary, that is 2 degree, to form the corresponding amides. Here are the examples. Ethyl chloroacetate when react with ammonia at 0 degree Celsius will give you chloroacetamide. and ethyl lactate will give you 2-hydroxypropanamide. Gamma valeriolactone when reacts with methylamine will give you 4-hydroxy and methyl pentanamide. Next reaction with hydrazine NH2NH2 to give the acid hydrazides along with alcohol. Example is also there. Next reaction is with hydroxylamine NH2OH. Esters react with hydroxylamine in the presence of ethanolic potassium hydroxide to form hydroxamic acid. You can see the general reaction and the example is also there. Next reaction is with Grignard reagent. Alcohols are produced here. Esters of formic acid react with 2 mole of Grignard reagent in dry ether to form secondary alcohols with 2 identical alkyl group. So, you can see the reaction how ethyl formate reacts with methyl magnesium iodide to give the addition product, and then it will give you acetaldehyde. It again react with methyl magnesium iodide to give the addition product, which on hydrolysis will give you propane 2-ol. And you can see the identical group in the product, that is in the alcohol. Esters of carboxylic acid other than formic acid react with 2 moles of a Grignard reagent to form tertiary alcohol, again with 2 identical alkyl group or aryl group. Here is the example: ethyl acetate when react with ethyl magnesium bromide will give you first of all addition product, then it will give you butane 2-on, again addition product will form, and which on hydrolysis will give you 3-methyl pentane 3-ol. Lactones react with 2 equivalents of Grignard reagent to form a cyclic diols. In the product, one of the alcoholic group is tertiary. So, you can see the example: gamma valeriolactone when reacts with methyl magnesium iodide, here we are taking 2 mole as we have discussed in the last slide also, and subsequently hydrolysis will give you 2-methyl hexane 2,5-diol. And you can also see the tertiary alcohol, that is the left terminal. Next reaction is the reduction. Reduction with lithium aluminium hydride, primary alcohols are produced. Esters on treatment with lithium aluminium hydride in dry ether and subsequent acidification yield primary alcohols. Lactones are reduced to corresponding diols. The reagent reduces many other functional groups such as carboxylic acid, anhydrides, acid halides, acid amides, nitriles, aldehydes, ketones and nitro groups. However, it will not reduce the carbon-carbon double bond if present. And you can see the example: ethyl pent 2-enoate when reduced by lithium aluminium hydride, and after hydrolysis will give you pent 2-enol, and methyl benzoate will give you benzyl alcohol. Gamma valeriolactone will give you pentane 1,4-diol on reduction with lithium aluminium hydride. Lithium borohydride also reduces esters to primary alcohols, but it must be noted that sodium borohydride does not reduce. Next reaction is the reduction with sodium and ethanol. It is Bouvelet-Blanc reduction, or we can say the preparation of primary alcohols is there. Esters are reduced to primary alcohols by treatment with sodium in refluxing ethanol. Here are the 2 examples: methyl propanoate will give you propane 1-ol, diethyl decane 1,10-dioate will give you decane 1,10-diol on reduction with sodium and ethyl alcohol. Catalytic hydrogenation. Esters can be reduced to primary alcohols by hydrogenation over copper chromite catalyst at about 250 degrees Celsius under a pressure 200 to 300 atmospheres. Here are the examples: methyl laurate will give you lauryl alcohol, ethyl phenyl acetate will give you 2-phenyl ethanol, diethyl adipate will give you hexane 1,6-diol. Next, reduction with the diisobutyl aluminum hydride, aldehydes will produce esters on treatment with 1 equivalent of diisobutyl aluminum hydride, in short form DBAL, in toluene at -78 degrees Celsius, and subsequent acidification will give you aldehydes. Lactones, that is cyclic, are reduced to corresponding hydroxyaldehydes. Here are the two examples. Ethyl dodecanate, dodecanol is produced, gamma butyrolactone will give you gamma hydroxybutyraldehyde. Next reaction is the condensation reaction. What is condensation reaction? When the molecules combined with the elimination of small molecule. The most important, Claisen condensation. The esters that contain at least 2 alpha hydrogen atom undergo self condensation in the presence of a base. Here we are taking the sodium alkoxide to form the beta keto esters. The esters that contain only 1 alpha hydrogen atom such as ethyl isobutyrate also undergo Claisen condensation in the presence of a much stronger base than the alkoxide ions such as triphenyl methyl sodium. Here is the example, ethyl acetate. Here we are taking 2 molecules, we have already stated, to give the ethyl 3-oxobutanoate when condensed with sodium ethoxide subsequently by hydrolysis. Another examples are also there. Ethyl propanoate will give you ethyl 2-methyl 3-oxopentanoate, and ethyl 2-methyl propanoate will give you ethyl 2,2,5 trimethyl 3-oxohexanoate. How the mechanism proceed of Claisen condensation reaction? First of all, the first step is the formation of enolate ion. The ethoxide molecule which obtained after the dissociation of sodium ethoxide will attack on the ester group to give the enolate ion. You can see how it gives the enolate ion. Next step is the nucleophilic acyl substitution of ester by enolate ion through addition and elimination mechanism. You can see the enolate ion first formed in the first step will attack to the another molecule of ester, that is the acyl group, and which on subsequent rearrangement to give the beta keto ester. Third step is the deprotonation of beta keto ester. How it deprotonate? By the ethoxide ion. And you can also see the conjugate base of beta keto ester or the resonating structure. Next step is the protonation of conjugate base of beta keto ester and will give you beta keto ester. Next is the cross Claisen condensation. When a mixture of 2 different esters, in simple Claisen condensation we have taken the 2 esters. Now we have to take, as the name indicate, crossed Claisen condensation, 2 different esters we have to take, each containing alpha hydrogen atom, and when treated with base, a mixture of self condensation products, 2 cross condensation product is obtained. However, cross condensation reaction may be synthetically useful when one of the 2 ester component has no alpha hydrogen. 2 condensation product, 1 cross condensation product and 1 self condensation product will be possible. The self condensation product is formed only in very small amount because the ester having alpha hydrogen is considerably less electrophilic at its carbonyl carbon other than the ester that has no alpha hydrogen. Here are the examples. Examples of ester that have no alpha hydrogen are formate, benzoate and oxalate esters. So, you can see the cross Claisen condensation examples. When ethyl formate, you can see there is no alpha hydrogen, when react with ethyl acetate will give you ethyl 3-oxopropanoate and ethyl benzoate, again no alpha hydrogen is there, when react with ethyl acetate will give you ethyl benzoyl acetate. Another example, diethyl oxalate, you can also see here there is no alpha hydrogen, will give you ethyl oxaloacetate. So, one molecule will contain the alpha hydrogen like ethyl acetate, while another will not contain like diethyl oxalate. It is called cross Claisen condensation reaction. Next type is the mixed Claisen condensation reaction, which can be carried out between an ester and a ketone, and the product is beta diketone or beta ketoaldehyde. Here is the example, when ethyl acetate reacts with acetone will give you pentane 2,4-dione or acetyl acetone. Few examples are there, cyclohexanone when react with ethyl formate will give you 2-oxocyclohexane carbaldehyde, that is aldehyde and ketone. Cyclohexanone when react with diethyl carbanoate, one ketone and one ester will give you ethyl 2-oxocyclohexane carboxylate. Cyclohexanone when react with diethyl oxalate, you can see the product, structure of the product, that is ethyl 2-oxocyclohexane carboxylate. Next is the intramolecular Claisen condensation. It is also known as the Dickmann condensation. The diesters of hexane 1,6-dioic acid, that is adipic acid, and heptane 1,7-dioic acid, that is pamelic acid, undergo intramolecular Claisen condensation reaction in the presence of a base, usually an alkoxide base, to form the 5 and 6 membered cycloketoesters respectively. And you can also see how diethylhexane 1,6-dioate will give you ethyl 2-oxocyclopentane carboxylate. First of all, you can see that ethoxide ion will abstract the proton from the one center of the ester, then this carbon ion will attack to the acyl group of the another ester molecule. So, there is a cyclization of open chain ring and followed by hydrolysis will give you the product. Next is the acylon condensation. When carboxylic acid esters are heated with sodium in an inert aprotic solvent such as ether, benzene, toluene or xylene, they undergo bimolecular reduction to form alpha hydroxy ketones, which are known as acylones. The initial product of the reaction is the sodium salt of an enediol, which on acidification gives the acylone. Here is the example, ethyl acetate when reacts with benzene, sodium, and after hydrolysis will give you 3-hydroxybutane 2-one, that is acetone. Acylon condensation is particularly useful for the synthesis of large cyclic acylones from diesters of dicarboxylic acid. You can see the diester of dicarboxylic acid, N value varies from 4 to 20 or it may be more, and you can see the structure of cyclic acylone and N can be vary. Now the uses of esters. Many esters are useful as artificial flavor and essences. The following are the important. Ethyl acetate is used as a laboratory solvent for reaction medium and extraction of organic compounds. Ethyl acetate and butyl acetate are used as industrial solvent for liqueurs, oils, fats and varnishes. Esters with a high boiling point and such as N-butyl phthalate used as plasticizers or we can say softening agents for resins and plastics. Esters are also useful for preparing various other compounds. For example, ethyl acetate is used in the preparation of ethyl acetoacetate and acetyl acetone. This is a table which shows the some of the compounds like isobutyl with flavor raspberry, esters isobutyl propionate with flavor rum, and with the isoamyl valerate with flavor apple, isoamyl acetate with banana, butyl butyrate with pineapple, and tertiary pentyl acetate with peer. Next derivative of carboxylic acid is the acid amides, that is the hydroxyl group of the acid has been replaced by the NH2 group, amino group, or we can also say carboxamides. The general formula of the acid amide having no substituent on the nitrogen atom is RCONH2. We can say this is the primary amides or simple amides. The amides that contain an alkyl or aryl substituent on the nitrogen atom of the amide group are called secondary amides, or we can also say N-substituted amide, while those that contain two substituent on the nitrogen atom are called tertiary amides, that is NN-disubstituted amides. These substituents may be identical or different. Here are the structures of primary amide RCONH2, secondary amides RCONH-R-, one hydrogen has been replaced by the R- group, tertiary amides RCON-R-2, one more hydrogen will be replaced by the R- group. Cyclic amides are called lactams. 5 and 6 membered lactams are readily formed gamma amino acids and delta amino acids on heating. They are called gamma lactams and delta lactams respectively. Compounds that contain a nitrogen atom bonded to two acyl group, you know the acyl group RCO, or aryl group, that is ARCO, or called amides. They have the functional group CONH-CO. The cyclic amides are the more important amides. Here are some examples. Gamma aminobutyric acid on heating will give you gamma butyrolactam, cyclic amide, succinimide or cyclic imide. We have already stated what are imide. RCO group, 2 RCO group attached with nitrogen. Delta amino caproic acid will give you delta caprolactam, and you can also see the structure of benzyl penicillin or penicillin G. Now the nomenclature of amides. The common names of primary amides are derived from the common names of parent carboxylic acid by replacing the suffix "ic" by the suffix amide. The IUPAC names are derived from IUPAC names of the parent acid by replacing the suffix oic acid by the suffix amide. When CONH2 is attached to a ring, the suffix carboxylic acid of the parent acid will be replaced by the suffix carboxamide. Here are some examples. In the brackets, common names are given. Methenamide HCONH2, the common name is formamide. Ethenamide, acetamide. Propanamide, propionamide. Butanamide, normal butyramide. 2-methyl propanamide, isobutyramide. 2-methyl cyclohexane carboxamide. Benzene carboxamide, benzamide. So you can see how the nomenclature has been done. In the case of secondary and tertiary amides, the names of this substituent on the nitrogen atom are written before the name of parent amide. These substituent names are preceded by the letter N, and nitrogen indicate that they are attached to the nitrogen atom. So here are some examples. N-ethyl ethenamide, you can see that ethyl group is attached to the nitrogen. So N-ethyl acetamide, because acetyl group is there. N-dimethyl methenamide, 2 methyl groups are there. N-dimethyl formamide, N-ethyl, N-2-dimethyl propanamide, because you can see the attached group to the nitrogen. N-ethyl, N-methyl isobutyramide. Now the preparations of amide. We can prepare the amides from acid chloride simply by reacting with ammonia and the derivatives of ammonia. Acetyl chloride react with ammonia to give acetamide, benzoyl chloride will give you benzamide, acetyl chloride when react with methylamine will give you N-methyl acetamide along with methyl ammonium chloride. Acetyl chloride when react with dimethylamine will give you N-dimethyl acetamide and dimethyl ammonium chloride. Benzoyl chloride when react with aniline, we will see the product. From acid anhydride, primary, secondary, tertiary amides can also be prepared by reaction of acid anhydride with excess ammonia, primary, secondary amines respectively. This method is less frequently used. So, cyclic amides are often prepared from cyclic anhydride by this procedure. So, here are some examples like acetic anhydrides when react with ammonia will give you acetamide along with ammonium acetate, aniline will give you acetanilide, phthalic anhydride will give you phthalimide, phthalic anhydride will give you N-ethyl phthalimide when react with ethylamine. Next, preparation from the esters of carboxylic acid. Esters also react with ammonia and amines to yield the corresponding amides. The method is rarely employed, however, it is synthetically useful in case where the corresponding acid chloride or anhydride is unstable or not easily available. These are the examples. Diethyl succinate will give you succinamide, ethyl lactate will give you lactamide. Lactamide cannot be prepared by the reaction of corresponding acid chloride with ammonia because attempted preparation of the acid chloride lead to a polymer formation. You can see the reaction. Next, from the ammonium salts of carboxylic acid, carboxylic acids are first allowed to react with ammonia or amines to form the corresponding ammonium salts. These salts are then heated strongly to yield the amides and the water. Water escapes as vapor and helps the equilibrium to move the forward direction according to Le-Chatelier principle. There are two examples, acetic acid will give you acetamide and benzoic acid will give you benzanilide when react with aniline. Another two examples are there, ammonium succinate will give you first of all succinamide and which will when heated at 300 degrees Celsius will give you succinimide. Ammonium phthalate will give you phthalimide and which will give you phthalimide on further heating. Now, from the carboxylic acid on being heated with urea yield primary amides by exchange of amide group. Acetic acid will give you acetamide and substituted amides can be prepared in excellent yield under mild conditions by treating with carboxylic acid with amines in dry ether or THF tetrahydrofuran in the presence of DCC, that is dicyclohexyl carboimide. It is a strong dehydrating agent. It helps the reactant to combine by removing a water molecule and itself get converted to N-dicyclohexyl urea. So, it is the example. First of all, acetic acid react with beta-phenyl ethylamine and DCC at 0 degrees Celsius along with the THF will give you N-beta-phenyl ethyl acetamide and itself converted to N-dicyclohexyl urea. This is the mechanism, how the mechanism proceed. First of all, acid will attack by the DCC to give the 1 degree amine and which will further after rearrangement to give the 2 degree amine or secondary amine along with the N-dicyclohexyl urea. Next, from alkyl or aryl cyanides. Primary amides can be prepared by controlled hydrolysis of alkyl or aryl cyanides, that is nitriles. This can be effected by dissolving the cyanide in concentrated H2SO4 and then pouring the solution into the cold water. The nitrile may be treated with dry HCl gas or concentrated HCl and then poured into the cold water. Alkyl or aryl cyanides can also be readily converted to primary amides by treating with hydrogen peroxide in dilute NaOH. So, benzonitrile will convert it to benzamide. This is the mechanism. First of all, as a protonation is there, then water molecule will attack to the carbon, and after rearrangement it will give you amide. How it takes place you can see in the slide. Another mechanism with H2O2, that is hydrogen peroxide. You can see how it will attack to the nitrile group, and first of all there is a protonation by water molecule, then it will attack to the carbon, the anion obtained by the dissociation of hydrogen peroxide, and it when reacts with water molecule and further rearrangement will give you the amide. So, overall reaction is the cyanide or nitriles when react with the hydrogen peroxide will give you the amide. Now, the physical properties of amides, that is RCONH2. Formamide is a colorless liquid, boiling point 211 degrees Celsius, melting point 2.5 degrees Celsius. All other primary amides are white crystalline solids. Primary and secondary amides are strongly associated through intermolecular hydrogen bond. You can see the hydrogen bond, intermolecular hydrogen bonding in amides. They are polar compound, they have high melting point, high boiling point, and even higher than those of corresponding carboxylic acid. For example, acetamide has boiling point 222 degrees Celsius, while acetic acid has boiling point 118 degrees Celsius. The tertiary amides have relatively lower melting points and boiling points because they do not form intermolecular hydrogen bond. Amides containing up to 6 carbon atoms are soluble in water due to the formation of hydrogen bond with water, and you can see how this amide form a hydrogen bond. The dotted line will show the hydrogen bond. Amides are soluble in organic solvents. Now, the important part, the reactions of amides. Among the acid derivatives, the amides are least reactive towards the nucleophilic acyl substitution. Why it is so? There are mainly two reasons. First is the resonance in amides is more prominent, which decreases the electrophilicity of carbonyl group, or we can say carbonyl carbon. On the other hand, minus I effect, inductive effect of the nitrogen is weaker, which increases the electrophilicity of carbonyl carbon only to a small extent. You can see the resonating structure of amide and how the inductive effect is increases by the N of amino group. This amino group is a poor leaving group because it is a strong base, weaker the base, better the leaving group. For the nucleophilic acyl substitution to take place satisfactorily, either NH2 group needs to transform into a good leaving group, or for example by protonation, or nucleophile must be very strong. So, it is the simple thing, if you want to substitute this amino group, it has to be better leaving group, or if you want to replace this NH2 group by the nucleophile, that is substitution, you want the substitution, the nucleophile must be stronger than this amino group. Now, the reactions of amides, acidity of amides, amidate salts are formed. The nitrogen, hydrogen in primary and secondary amides are weakly acidic because the amidate ion, that is, what is amidate ion? RCONH, one proton is abstracted from there, is somewhat more stabilized by resonance than the amides. Following reactions leading to the formation of amidate salts indicate the acidity of hydrogen attached to the amide nitrogen. So, you can see the reactions. Now the basicity of amides, acyl ammonium salts, formation of acyl ammonium salts. Amides are expected to behave as bases. Why it is so? Because the presence of lone pair of electrons both on nitrogen as well as oxygen atoms. Amides are considerably more basic than carboxylic acid derivatives. However, amides are much less basic than amines because the lone pair of electrons on nitrogen atom of amides are delocalized with the pi electrons of the carbonyl group. And you can see in the reaction the resonance, the delocalization of lone pair of electrons on nitrogen atom along with the oxygen atom. Amides form salts with strong inorganic acids. With dilute acids, the protonation occurs only to a very limited extent. The protonation occurs at the oxygen atom rather than the nitrogen atom. Why? Because only then the conjugate acid is stabilized by the resonance. The protonation at nitrogen would give a cation, that is RCONH3, and you can see which is not stabilized by the resonance because there would be no lone pair of electrons on nitrogen atom for conjugation with carbonyl group. So, this reaction will show the conjugation of lone pair of electrons on nitrogen with the oxygen on carbonyl group. Next reaction is the hydrolysis. Unlike acid chlorides and anhydrides, amides are particularly not hydrolyzed by water alone. Acid amides are hydrolyzed to carboxylic acid and ammonium salts by heating with aqueous mineral acid, that is HCl. Simple reason is that because these were the water molecule were the weak nucleophile as compared to the amino group. I have already stated, if you need to substitute this amino group, you need a stronger base or strong nucleophile in comparison to this amino group, NH2 group. So, you can see there are two examples. Acetamide will give you acetic acid, N-methyl benzamide will give you benzoic acid and methyl ammonium chloride. Amides are much more readily hydrolyzed by heating with aqueous alkali to yield the carboxylase salts and ammonia or amines. Here are the two examples. Acetamide will give you sodium acetate, N-methyl benzamide will give you sodium benzoate along with the methyl amine. This is the mechanism of hydrolysis by acid catalyzed and by alkaline hydrolysis. You can see in the acid catalyzed, first of all, protonation of carbonyl group will takes place. Then there is a attachment of water molecule to the carbonyl group. Then there is a elimination of NH4 ammonium ion by the proton atom. Next mechanism is the mechanism of alkaline hydrolysis. As we are saying, alkaline hydrolysis, hydroxyl group is there to attack on the acyl group of the amide group, and it will abstract the proton from the hydroxyl group which is attached to the acyl group. Then there is a rearrangement, or we can say elimination of ammonia molecule. So, here is the common reaction. Acetamide will give you acetic acid on hydrolysis with HNO2. Next reaction is the Hofmann-bromamide reaction. When primary amides are heated with bromine and alkali, they are converted into primary amines containing one carbon less than the number of carbon atom present in the amide. So, you can see the primary amide RCONH2 when react with bromine and NaOH will give you primary amine, that is RNH2. This is also called Hofmann-bromamide reaction or Hofmann rearrangement because rearrangement will take place during the mechanism. It is also known as Hofmann degradation of amides because in the amine one carbon is less than that comparison to the amide. These are the examples. Acetamide will give you methylamines, benzamide will give you aniline. Phthalimide will give you anthranilic acid, and again you can see that beta aminopropionic acid is formed by this cyclic amide. How mechanism takes place? You can see, first of all, there is a abstraction of proton by the base, then there is a elimination of bromide ion, then this R group will migrate to the electron deficient nitrogen. A chiral R group migrates with retention of its configuration. Retention of configuration means if it is R, it will be R remain in the product, and if it is S, it will remain S. After rearrangement, we will get the alkyl isocyanate, which on hydrolysis will give you primary amine after carbamic acid. So, this reaction also occurs with chlorine and with alkali. Next is the dehydration of primary amides. When primary amides are heated with an efficient dehydrating agent, that is P4O10 or POCl3 or SOCl2, they lose a molecule of water to form the corresponding nitriles. There are two examples. Acetamide will give you acetonitrile, benzamide will give you benzonitrile. Next reaction is the reduction of amines. Primary, secondary and tertiary amides on reduction with lithium aluminium hydride yield primary, secondary and tertiary amines respectively. The carbonyl group of the amide is converted to the CH2 group, methyl group. Similar conversion can be affected by hydrogen in presence of nickel catalyst. So, here are some examples of reductions of amides to the corresponding amine, that is acetamide will give you ethyl amine when reduced by lithium aluminium hydride, and methyl acetamide will give you ethyl methyl amine, and then diethyl acetamide will give you triethyl amine. Cyclic amides, that is lactams, cyclic amides are known as lactams, on reduction with lithium aluminium hydride will give you cyclic amines. You can see the example, gamma valerolactam when reduced by lithium aluminium hydride, it will give you 2-methyl pyrrolidine. Now the uses of amides. Amides are useful for preparing amines. Primary amides are useful in preparing nitriles, and then dimethyl formamide is very useful as a polar aprotic solvent in organic synthesis, and then diethyl formamide is used as a formylating agent. In the presence of POCl3, it introduces CHO group, that is formyl group at the ortho and para positions of the phenolic ether, and then dialkyl anilines. It is called Willsmer-Hack reaction. Methyloxybenzene when reacted with dimethyl formamide in presence of POCl3 will give you para-methoxybenzaldehyde, that is N-acetaldehyde. So, that is all for the reactions of amides and esters. In this way, we have discussed about the derivatives of carboxylic acid, that is esters, anhydrides, amides and esters. Thank you so much.
With this note, thank you ma'am, thank you so very much. Dear friends, if you have any queries or if you want to give any kind of feedback, you can mail us at info.cec@nic.in, and the very next time we would be coming again and we would be continuing this series further. Thank you ma'am, thank you so very much.